Hi everyone, thank you for attending our talk today. My name is Christian and I'll be presenting some of our work on the Puckboard project. This project is part of the MIT Air Force Accelerator, which is a collaboration between the Air Force, MIT, and Lincoln Laboratory. The motivation for this problem is that Air Force mission and training scheduling is a complex, time-consuming, and mostly manual process. A typical schedule can take 3 airmen working 9 hours a day for a total of 27 person-hours to develop. In fact, the project name Puckboard comes from the legacy system of shuffling pucks around a whiteboard to find schedule solutions. Our goal is to not only assist the schedule makers, but also improve the quality of the schedule for the personnel. Here's a rough outline of my talk today. I'll note some relevant work, then review the flow of the current scheduling process. After talking about the data available, I'll discuss our formulation and how we incorporate 2 key factors: overqualification and training requirements. I'll conclude with some interesting ongoing and future work. I'll now briefly cover some relevant related work. There was a master's thesis in 2018 that looked at the problem of naval flight training scheduling. There is also extensive work on integrated event and crew scheduling, particularly related to the commercial airline industry. There is also a host of other literature in other domains, like airport staffing, hospital staffing, mail sorting, and so on. Here's an overview of the entire scheduling process. There are 2 main steps in the scheduling process in green. The first is event scheduling, which is deciding when each event is, how long it is, and with which aircraft it is. The second is crew scheduling, which is assigning personnel to each event. Focusing on event scheduling, there are 3 main types of events: simulations, which happen on the ground, training flights, and missions. Simulations are generally managed by contractors, and the Air Force pays them for time on the sims, so these are known well in advance. In addition, there's not much flexibility in moving these events around. Training flights are also scheduled well in advance. Missions have a shorter lead time, and urgent missions often pop up with little notice, throwing previously made schedules into disarray. Managing and mitigating disruptions from last-minute missions is a future goal of ours. Aircraft availability constrains the event scheduling process. In addition, crew qualifications and availability are loosely considered during event scheduling, but this is very difficult because event and crew scheduling are often determined by different people or even different departments. In this talk, I will focus on the crew scheduling portion. The scheduler gathers the scheduled simulators, training flights, and missions from various databases. They then fill vacancies based on crew availability and crew qualifications, as events have different required qualifications. Crew availability can be tricky for schedulers, as it is constantly changing and the database is not always up to date. Thus, schedulers occasionally have to call, text, or personally track down personnel to confirm their availability. Besides crew availability and crew qualifications, schedulers must consider the training and simulation requirements of the crew. For example, a pilot may need to complete 2 night flights and 2 air jobs in the next 3 months. They should thus be assigned to events that satisfy these requirements. One of the challenges of this project has been pulling together reliable data. There is no consolidated place where all of this data lives, so considerable effort is required to aggregate across different data sources. For events, we have the start and end times, including the pre-event briefing and post-event rest. We have the minimum and maximum number of personnel for each event. Simulations usually have fixed capacity, but training flights and missions can have a wide range of capacities. We also have the crew qualifications required for each event. For example, several training flights require highly qualified instructor pilots on board. For personnel, we have their qualification levels at any given time, which dictates which events they can be assigned to. We also have availability, which includes data on vacations, additional duties, temporary duty travel assignments, and so on. Finally, we have training requirements that each personnel must complete. Now, I'll walk through a mixed integer linear formulation for the crew scheduling problem. We first define sets for pilots, flights, time periods, types of requirements, which could be certain simulations, training, or mission types, and qualification levels. Several subsets will be used in the constraints or objective function. I won't go through all of them here, but I'll highlight some of them in the following slides. We also have our decision variable, which indicates whether a pilot I was assigned to a flight F. We start with two basic constraints, the first being the maximum number of pilots for a flight, and the second being the minimum number of pilots for a flight. It may be desirable to exceed the minimum number of pilots to satisfy additional training requirements. The third constraint ensures that each flight is staffed with appropriately qualified crew. The indicator variable Z is 1 if pilot I satisfies qualification J, else it is 0. J is a qualification required by flight F. We multiply this variable by the decision variable X of whether pilot I is assigned to flight F, and the sum of this across all pilots must be greater than or equal to Q, which is the number of personnel with qualification J required for flight F. There's a subtle detail here such that Q is the number of personnel required for qualification level J or higher. Consider an example with 1A and B pilot required, with A being higher than B. If we set Q for A and B to both be 1, we could satisfy this requirement with just one pilot level A, as it would satisfy both constraints. Thus, we must require 2 of level B or higher and 1 of level A or higher. We next go over 2 availability constraints. The first is that crew cannot be assigned to overlapping flights. The set U gives the flights that overlap with a given flight F. The second constraint is that crew cannot be assigned to flights during time periods for which they are unavailable. The time-dependent variable T is 1 if pilot I is available during time period P, else it is 0. P is all the time periods that are contained in flight F. Now we move on to some unique constraints that are necessary to incorporate training requirements in the objective function. The first 2 constraints help define a variable R, which is 1 if k number of requirements of type S are satisfied by pilot I. This variable will be used to reward training requirements completed in the objective function. We say that the number of requirements completed, which is the sum of these R variables, must be less than or equal to the number of requirements S needed by pilot I. Moving on to the second constraint, the sum of requirements completed must also be less than or equal to the number of flights that this pilot completes of type S in this time period. Finally, we have a constraint that helps define the order for which the R variables are set to 1. If 2 requirements are fulfilled in this time period, then that means 1 requirement also has been fulfilled. In variable notation, this means that if R sub 2is is 1, then R sub 1is also must be 1. We now look at how training requirement completion is incorporated in the objective function. We reward each requirement completed based on the number of requirements remaining when it was completed. For example, if 1 requirement was completed and there was 1 requirement remaining, we give a reward of 1. If there are 2 requirements completed and there were 4 remaining, we reward 4 to the first requirement completed and 3 to the second one. We also incorporate overqualification into the objective function. Overqualification is when a highly qualified pilot, like an instructor pilot, flies an event that could have been staffed by a lower qualified pilot. More qualified pilots tend to be more senior, and it is important to keep highly qualified pilots available for pop-up missions. Thus, in this maximization formulation, we assign higher qualified pilots a more negative penalty, so that we will tend to choose lower qualified pilots before higher qualified pilots. The constraints mentioned before ensure that no underqualified pilots are assigned to events. These penalties are also normalized to be between 0 and -1, so that requirement completion takes precedence over overqualification. Here we present a quick sensitivity study on the training reward. We showed the linear reward for a requirement completion, where the reward is based on the number of requirements outstanding. However, we can also give a constant reward of 1 to every requirement completed and not favor any number of requirements remaining over others. We run our scheduling formulation over 14 two-week time periods. The y-axis shows the frequency of outstanding requirements when filled, and the x-axis shows the time periods. The linear reward is in solid lines, and the constant reward is in dotted lines. We see that the linear reward initially favors filling the 2 outstanding requirements in red more than the 1 outstanding requirements in blue. After time period 5, the linear reward has most pilot event combinations only having 1 outstanding requirement. In fact, in the last 2 time periods, the linear reward results in at most 1 outstanding requirement. This is good from the standpoint of robustness, as pilots are close to being up to date with the requirements well before the last time period. We have a lot of ongoing work that I did not get a chance to touch on. First is incorporating more sophisticated requirements, such as those with a due date or rolling requirements that are required X months since the last time of completion. We also recognize that events are not guaranteed to satisfy training requirements. For example, an airdrop portion of a flight may be canceled because of inclement weather. And of course, crew and aircraft unavailability can derail schedules. We are looking at using reinforcement learning for scheduling. This may be better suited than the mixed integer program to react to disruptions. The difference is that with reinforcement learning, we have an agent that explores by interacting with its environment and learns the best way to maximize reward. Here, we have an agent that is rewarded for the same things as the MIP and penalized when it reaches an infeasible state, such that it cannot fill an event with crew. Finally, We are looking at embedding schedules into smaller dimensions to estimate schedule similarity. This could be useful for providing schedulers with multiple options and allowing them to compare them and identify how close they are. This could also help with disruption recovery, as you would want to move toward a schedule that is very similar to the current one, but still feasible. I've attached a summary slide, but I won't talk through it. That concludes my talk, and thank you for attending and listening, and I am happy to take any questions or comments.